Okay, stepwise optimization. Let us start with a maximization problem with only two choice variables, k2 and k3. Take anything. Let's say k2 is the amount of knowledge you want to have at the beginning of the second year of your college, and k3 is the amount of knowledge you want to have at the beginning of the third year of your college. And you want to maximize function f of k2 and k3, so f is, for example, the amount of fun in life you have. And that maximization is subject to some constraint. It's by no means a very rigorous argument. But if you want, you can assume that f is continuous and the c is nicely compact and so on. It doesn't really matter. So let's say the constraint set C looks like this. So we should find a pair k2, k3 within this set. And suppose the optimum is around here. Finding a solution in the two-dimensional space is something like searching the floor of your room for a lost contact lens. Now, one secure method of searching, which is not necessarily an efficient method, is a line-by-line, row-by-row search. And that's what we mean by stepwise optimization in today's class. Let's see. Let's fix k2. Let's fix k2 at 3. Then we can focus our search on this segment. Within this segment, which point maximizes our objective f? In other words, if k2 is equal to 3, then what's the value for k3 that maximizes the objective f? Let's say if k2 is equal to 3, then optimal k3 is around here, so that if k2 is equal to 3, then this is the point that maximizes our objective within this segment. Similarly, suppose we fix k2 at 1 and focus our search on this segment. What is the corresponding best k3 in this case? Suppose the best point is here, so that within this segment, this is the point that maximizes f. And you do this for all possible k2s. You fix k2 and find the corresponding best k3. And after doing this, the candidates for the solution to the original problem are narrowed down to this curve or line. So the search is no longer two-dimensional, it's one-dimensional problem. You look for the best k2 within this set. This is the set of k2 for which there is some k3 such that the k2 and k3 together fall within this set C. Such set is sometimes called the projection of C onto the k2 coordinate. So you look for the best k2 within this set and reach the solution. Okay, this is the best level of k2. The point is that when you're looking for the best k2 within this set, your search is along this line. So your search is no longer two-dimensional, it's just one-dimensional problem. Let me explain this idea with mathematical expressions. So for each k2, find k3 to maximize the objective function f with that given k2, subject to the fact that the given k2 and the chosen k3 together fall within the constraint set C. The problem is one-dimensional because k2 is fixed. If you solve this problem for each possible k2, then the optimal k3 you find is a function of k2, because k2 is given. Once you get the optimal k3 as a function of k2, then substitute this function into the objective, so that the objective function is just a function of k2 only. Now let's find optimal k2 that maximizes this. Now the maximization problem is a one-variable maximization, and the search for k2 is within the projection of the constraint set C. In other words, there must be some k3 such that the k2 and k3 together fall within the constraint set. By solving this problem, you obtain the optimal k2. Once you get the optimal k2, plug it back into this k3 function, and the corresponding K3 is obtained. Now you might have noticed that this process of step-by-step optimization is very much like backward induction. To see why this process resembles backward induction, let me nest these two maximization problems to put them together. First, choose K2, and whatever K2 is chosen, K3 should be chosen optimally, depending on K2. So the choice of K3 is the inside of the choice of K2. And when we solved this problem, we started from the end, as in backward induction. That is, provided that K2 is somehow chosen, choose K3 optimally. And of course, that decision depends on K2. And as the second stage, choose K2 optimally so that this whole thing is optimized. This is what I mean by the idea of stepwise optimization is pretty much like that of backward induction. What if we have more than two choice variables? So we have not only K2 and K3, but also K1. So the objective is a function of three variables, and these three variables must satisfy constraints. The idea is the same. First, we can fix K1. Once K1 is fixed, then the problem has only two variables, K2 and K3. And we already saw how to solve a two-variable problem by stepwise optimization. Suppose you fixed K1 at 1.3, then the constraint that K2 and K3 must satisfy might look like this. Using the stepwise optimization, suppose you find the optimal solution K2, K3 here. And you do this for all possible K1. So you change K1 every time you have two-variable problem, and you solve the two-variable problem. And you do this for all possible K1s. So this is the idea. First you fix K1, find optimal K2 and K3. Of course, the solution depends on K1, and you do this for all possible values for K1. And after that, the choice of K1 is a one-dimensional problem, so it can be easily done. If we express that process in the form of nested maximizations, it's almost like the two-variable case we have seen previously, but now we have one more nesting here. First, K1 is chosen. Given the chosen K1, K2 is chosen. And given K1 and K2, K3 is chosen. But when we actually solve it, we start with the innermost maximization and move outwards. That is, the stepwise optimization is basically backward induction. The stepwise optimization may be philosophically useful because it is basically the continuous variable version of the backward induction method, but it is not very practical or computationally efficient because basically you are searching the space line by line. However, there is a situation that stepwise optimization is actually practical or useful. And that is when this original problem satisfies some sort of time separability conditions. So let's have a look at that next. Suppose the objective function f can be divided into three parts. The term that depends on k0 and k1, and the term that depends on k1 and k2, and the term that depends on k2 and k3. By the way, k0 is just a given initial state. So we have nothing we can do about k0, it's just given. Importantly, suppose that there is no term that depends both on k1 and k3. Suppose also that the constraint can be divided into three small constraints. The constraint that the initial state and k1 must satisfy together, the constraint that k1 and k2 together must satisfy, and the constraint that k2 and k3 must satisfy together. Let's also assume that there is always at least one choice. That is, given the initial state k0, there is at least one value for k1 that we can choose, and whatever k1 we choose, there is at least one K2 we can choose. And whatever K2 is chosen, there is at least one value for K3 that we can choose. There may not be two choices, but there is always at least one choice. So it's very weak condition, because in daily life, whenever we say we have no choice, what we actually mean is there is only one choice. Okay? Usually there is always at least one choice. And this requires only that. So given these separability conditions, let's see how this nested version of the maximization problem can be rewritten. So I substitute this objective function and the constraint into this problem. Then the problem should look like this. Now the objective is the sum of the three separate functions. And you might notice that in the innermost maximization problem in which K3 is chosen, the first two functions are irrelevant because they don't depend on K3. So we can take these out of the maximization problem. Also, out of these three constraints, only the last one involves K3. So we can erase the first two constraints. Let me do that. Now let's move on to the maximization problem in the middle, in which we choose K2. The first term of the objective doesn't depend on K2, so we can take this out of this maximization problem again. And out of these three constraints, the first one doesn't involve K2, so it can be eliminated. Also, under our assumption, whatever feasible K2 is chosen, there is at least one K3 that satisfies this last constraint. So we can eliminate this last constraint as well. Only the second constraint remains. Finally, let's look at the outermost maximization in which K1 is chosen. Out of these three constraints, the second one and third one can be eliminated because we assume that whatever feasible K1 is chosen, these two constraints can be satisfied for some K2 and K3. So only one constraint is left. Now this stepwise maximization problem has got much simpler. In particular, if you look at this innermost maximization problem, this doesn't depend on K1. K1 is fixed, so in general, the optimal K2 and K3 should depend on K1. But this part depends only on K2, not K1. Similarly, if you look at this maximization problem in the middle, in which K2 is chosen, the solution depends only on K1. It doesn't depend on K0. In that sense, this nested maximization got much simpler under these separability conditions. Given that the solution to this innermost maximization problem depends only on K2, but not on K0 or K1, denote the maximized value of this maximization problem as V2, and this depends only on K2. K0 and K1 are irrelevant. Also, denote the maximized value of the second maximization problem as V1. K1 is given to this maximization problem, so the maximized value depends on K1, but not on K0. Finally, denote the maximized value of this outermost maximization problem as V0. And this maximized value depends on K0. Again, what's the definition of V1K1? V1K1 is the solution to the maximization problem in which K1 is given and K2 is chosen, and in which the sum of F2, K1, K2 and this whole thing, V2, K2, is maximized. Okay, that's this. Similarly, what is the definition of V0, K0? V0, K0 is the solution to the maximization problem in which K0 is given and K1 is chosen, and in which the sum of F1, K0, K1 and this entire thing, V1, K1, is maximized. Now you can see Bellman's optimality principle. That is, at each stage and given state, the best value can be achieved by maximizing the sum of the immediate payoff or immediate return and the next stage value, which in turn can be achieved by the optimal behavior starting at the next stage. And that's the case at each stage. This is the finite horizon version of the dynamic optimization problem in the Stokes-Lucas-Prescott framework. The initial state k0 is given, and you choose k1, k2, k3, k4 up to k capital T to maximize the sum of period returns. At each date, the return is function only of today's state and the next date state. And at each date, two adjacent k's must satisfy a constraint. This problem has exactly the same separability conditions that we have seen, and therefore the stepwise optimization can be well applied, and we have this nice functional form. That is, if we denote the maximized value at date t as b of t given the state kt, that is given by maximizing with respect to next date state the sum of the immediate return and the next date value. Okay?